a bunch of guys, failed this test. Yeah, my test is exactly one I dot, for which I'm greater or equal to tau for I dot, and less than tau for all the other guys. And I'm getting a bound on error here. Right? Look at these union bounds.
I star and Q star.
I star and what?
And Q star.
Oh, is there a Q star?
Q star in the diagram between the P and the Q.
No. Q star is just no. Q star is a probability mass function. I star is just an index. Yeah. The Q star is just something for analysis. You can erase Q star. Q star was something that we used in our analysis last lecture, but it's not important in today's lecture. Okay. Yeah. So again, I mean, there's this big vector that was sent over this communication channel. I got this noisy version of it, and now I'm looking through my dictionary and trying to see what it's closest to, and I'm measuring closeness through this weird test. Yeah.
Is it to say that we have a Q set for every single one of these indices?
What's that?
Like we have a Q, one of these Q balls, one of these Q sets.
But no, they're all the same because they all have the same distribution. Basically, there's a hypothesis testing problem, but it's an identical hypothesis testing problem for every I. For every I, you say, is it here or here? Now I know that only one thing is true, so it makes it's not really, they're not independent hypothesis testing problems. But I'm treating them as independent hypothesis testing problems just to apply the theory from Tuesday. But then I get these, So I could do much better if I could somehow use the fact that only one thing was sent, But you can get away with these crude bounds because what I'm going to do here is I'm going to use a union bound. Oh, wait. Yeah, I forgot to say I not equal to I star. All right, so the probability of a union is always less than equal to the sum of the probabilities. It's a quality if they're disjoint events, which they're not. But all of these guys have the same approximation, right? So there's n of them, and they all have the same approximation for each of them. It's n times, you told me, what is it again? Yeah, it's whatever this size of this guy is.
That's just the entropy, right?
Nope.
Or 1 over the entropy?
No entropy here.
For e to the minus nd?
No entropy here. No, it's not. Let's just, we have 10 minutes. Let's not blow it. It's not the entropy. Okay. We'll get to relative entropy in a moment. I mean, this was a set of all probability mass functions. No, I wrote it down before. Come on, it's right there. Q is the set of all probability mass functions whose, forget it. D was just a number. D was chosen so that this was, away from Q. That's all. But you can see I'm trying to make it big because right there you see it. N was e to the nr. Right? I mean, I had an integer part, but screw that. Let's not worry about integers. This product is e to the minus n d minus r. And that's what, we want to make d as big as possible, which means we're going to have to force that epsilon to be small. We're trying to make this ball huge, so we can deal with this stupid union bound. All right, and so, but you can see that this will go to 0 geometrically fast. If r is less than d. And how big can d be? Here's where you get to say relative entropy. How big can d be? you know, I can make this bigger and bigger and bigger and bigger until these guys just meet. And how big is that?
The entropy of the wall.
The relative entropy between Q and P. So if I make D equal to the relative entropy between Q and P, that's no good. It's no good because we fail on the first test. We're basically growing this I should have used a different colored pen. If we made D so big that we just touch Q, we'd screw ourselves here. But at least that gives us a bound. If we can get arbitrarily close to that, we could make epsilon arbitrarily small, which means we'd be making D arbitrarily close to R star, which is its relative entropy. Okay? So R is less than R star, or less than R star, which is the relative entropy between Q and P, between Q and P, and Q was the joint distribution. Did it. 4:44, 30 minutes. You can prove the coding theorem. You can prove at least half the coding theorem. So this is the coding theorem. I mean, half of it. That if you have a rate which is less than the mutual information, if you have a rate which is less than the mutual information, then you can send data with error that goes geometrically fast with the size of the code book. You know, it's amazing. It's in the geometry just says it. It's like nothing. You just have to learn the geometry. Do you see that? And look at the crappy bounds we used to get it. Can you believe this is tight? You know what I mean? You think this would be a really lousy bound, but it turns out you can actually prove this is tight. You know?
Really poor.
In general, it's usually poor, but here it's not. So you can actually show this is tight. Yeah. So we proved achievability, that if the rate is less than mutual information, then we can reliably send data. And of course, this is ridiculous. You'd never do this particular test. So of course, you could have chosen a lousy distribution for x. You could have chosen it to have zero entropy. It could have been just a delta function, so there's only one code word. The mutual information then would be zero. You know? And so that the channel capacity is to maximize this over all marginals px. You know, because you take a look at this. This is just a function of px. Because this joint distribution is just a function of px. It turns out this is a concave function of px. You can show that. So this is a beautiful, you know, convex optimization problem. And so there's really nice algorithms to solve this. Take a convex optimization problem, a class. And in fact, my favorite algorithm is my own. There's a but there's a bunch of algorithms for doing
Is
this.
that a double sum, the sum over all x and y? Or
Yeah. Yeah, that's right. Yeah, because our probably all these p and q were probably measures on the joint on the input output space x y. So what can you tell me about entropy? So entropy came up. I've got r is less than r star. Can anybody think of another bound on how big the codebook can be? How many code words are there? Possibly. What? Yeah. So we know that n is less than e to the minus e to the n hpx. Because we said that we said that the probability law on sequences of length n is approximately uniform on this many symbols. That was one of the things we proved. This is how many possible code words you could actually see. That was one of the things we proved.
That's the AEP, right?
That's the AEP. I should put less than equal to. And in fact, you can prove that. It's really easy to show that the mutual information is actually equal to the entropy minus something. There's no way to go into this any further. I just want to say if you take an information theory class, they will actually maybe define mutual information this way. It's the entropy minus the conditional entropy of x given y. All right? So you can find, again, take an information theory course. And so it is strictly less than hpx. Because conditional entropy is going to be positive. And so you get that. So it all fits together. And that is it, I think. What time, how does it work on, I think it's over now, right? I've got 5 minutes, cool. Any questions? Shall I prove the rate distortion theorem, or no, it's amazing. Their error exponents comes out of this like nothing. What's really cool, by the way, this is tight. There's a form of error exponents that you can get from this as well. It's not tight. It's an open problem whether it's tight or not. So there's some cool math problems here. Yep.
So I didn't understand why you said if D is the relative entropy, then it's not going to be included.
What?
Like if D is...
Well, D is the relative entropy. No, I just said that, no, I was running out of time. D is the relative entropy between Q star and P. I don't want to go there. D is just a number. D was just chosen to be less than the mutual information. I didn't tell you yet. I just showed you geometrically. I wanted to make sure this ball did not contain Q. That's all I did. Yeah. Okay. So by the way, what happened? All these people developed this beautiful mathematics. And what happened when computers were finally fast enough to apply it? Did people go and do maximum likelihood decoding? It was a crisis because we had all this math and no way to use it. And in a few years, they developed all this incredible linear coding theory. So they don't use maximum likelihood decoding. They have all these clever tricks. And they achieved that capacity through linear algebra tricks and all sorts of wild mathematics that has nothing to do with probability. So the probability gave you the bounds, like the gold standard for what you could achieve using some combinatorial nightmare decoder, which you could never apply. But then people with different expertise came up with crazy coding schemes to achieve it. It's like a miracle. I don't know anything about it, so don't ask me anything about these schemes. But and a lot of it was done at Illinois when I was there. So it's like, it was incredible. I started there in '89. And in the 90s, it was insane what happened at University of Illinois. Ralph Cotter was one of the leaders in this, and people were visiting from all over the world to Illinois. It was a crazy time, and then 90s were over, that was it. But so that's why I love this topic, because it's like it took collaboration from people with totally different backgrounds. Now, I've never had the energy to look at all the algebraic coding theory that went into making this feasible. I mean, your phones are based on all this crazy abstract nonsense. It's beautiful. Okay, so the plan now, I think I'm going to do it to you. We're going to actually prove Sanov's theorem, basically, Cramer's theorem, only because the tools are useful in other domains. It's not because I think you should be mathematicians. The idea of a change of measure for doing analysis comes up in analysis of all sorts of algorithms. And so it's a trick that is useful. Okay, so I think I will torture you with that. There's no way I could give it to you in a test. So if you want to skip it, you could, but you'd be missing out on a lot. Okay, but I'm going to have to be in New Orleans on Tuesday. So on Tuesday, we're going to have a treat from Aditya, who's going to give you a crash course on basically reinforcement learning. But you guys half of you don't know what control is. So just the foundations of reinforcement learning. So stochastic approximation, which is what reinforcement learning today is. So he's going to do that. It'll be a nice practice of law of large numbers tricks and refinements and CLTs. So it's very complementary. And he'll prepare notes for that as well that they'll distribute. But I guess that's all for today. Except for there's a question. Yep.
We have to quiz
And the quiz, thank you, yes. Yes to the quiz. I will send out some information to make it formal. I just want you to know the basics, what omega FP is, and what we meant by these conditional expectations and all that. I want to force you to just review that material in chapter 1. So it's just chapter 1, it'll be short. I'll broadcast information, but yeah. None of this. None of this. None of this. None of this. Just the basic basic abstract probability from chapter 1. Yeah. All right. So not like, I don't want you to integrate a density. I want you to know what what I mean by calligraphic F. I want to make sure we're talking the same language.